Oh, hey! Greetings and stuff and things. Welcome to some more stuff with integrals. We have so far kind of just played with indefinite integrals, the opposite of taking a derivative. And now we're going to look at a definite integral. When we played with derivatives, we knew that the derivative represented a rate of change. It has a graphical representation. It's essentially the slope at any given point. An integral also represents something graphically, and that is the area. If you've got some curve and you want to talk about what's happening on that curve underneath it, that's where the integral comes into play. In a definite integral, we set some bounds. We say, we're going to go from this starting point to this ending point. And underneath that curve is a whole bunch of area. And that's what's represented by a definite integral. And it's always what's above the x-axis, and below the function. So that's that definition. And we have a means of computing it. Now it's defined this way. We've got this little a and b thrown in to show the bounds of the integral. We're going to take the area from x is a to x is b. So in my cute little diagram up here, it's kind of like that first line would be a, this second line would be b. Those are the bounds. That's what we're taking this integral over. And all we have to do is find the antiderivative of this. We have to integrate it and then plug in a and b. So it's actually not so bad. I don't mind finding definite integrals. Definite integrals are pretty good times. So process-wise, we look at something like this. We want to evaluate this definite integral. We want to essentially find the area. You're right, I should write some stuff out. The area under negative 3x squared plus 4x plus 4 between x being 0 and x being 2. You don't have to write that out, but that's what it means. That's what we're doing when we find this particular integral. We're finding the area under this function between x is 0 and x equals 2, so over these particular bounds. Process-wise, first of all, we're going to find the antiderivative of that thing. I'm going to put it in some nice square brackets for reasons we have no idea why. But integrating this, okay, negative 3x squared must have come from some sort of x cubed. So I'll divide this by 3. All right, that's that. The 4x must have come from some sort of x squared. So I'll divide this by 2. Neat. And the 4 must have come from a 4x. That's stuff we can do. We're going to evaluate this particular thing from 0 to 2. So this gets thrown in. That's why those little rickety brackets are there, the square braces. Just so we can say we're taking that whole entire expression from when x is 2, or from x is 0 till x is 2. At this point, it's just a little bit of plugging in. So we're going to take this expression when x is 2 plus 2 times 2 squared plus 4 times 2. And we'll subtract what it is when x is 0. Boom! And now it's just an evaluation process. You can take this in a whole bunch of lines, or you can take this in fewer lines. You can use scrap paper if you want. Or how much room do we have? So much! Taking as many steps as you want. This is like -8 plus 8 plus 8 minus 0 plus 0 plus 0. Neat. Okay. So then really this is just 8. Wow! That was what we call fun. I dare you to try example B. Check your skills. Pause this video if you need to, or even if you don't, just pause it. See what you get. And then resume in like, I don't know, a few minutes. Assuming you've paused, I'm jumping back in. I'm going to evaluate this particular integral from -3 to 1. So this is equal to the antiderivative of the thing. So that came from x cubed. Pen sketching. Help. X cubed. But it must have been 2x cubed. Derivative of this is for sure 2 times 3 is 6. Drop the exponent, power 2. Excellent. And then antiderivative of -2x is -x squared. And I'm going to take this from a bottom value of -3 to a top value of 1. Now I plug in. So we're going to take this whole expression when x is 1, and we'll subtract what it would be when x is 3. 2 times 1 cubed minus 1 squared minus 2 times -3 cubed minus -3 squared. Oy. Didn't foresee myself taking powers of 3 today, but here we are. This is 2 minus 1 minus, oh boy! Alright, -3 cubed is -27. This is -54. Oop. And -3 squared is 9, so we're subtracting 9. Yeah, I might just take a couple extra lines for this just to make my life easier. -54 minus 9 is -63, I hope. And, okay, so then this whole thing is 64. The end of the whole lesson, except for the other page, which is over here. What we've done is use what's called the Fundamental Theorem of Calculus. As long as this function here is integrable over this interval, which is the opposite, the other direction of being differentiable over that interval. So you have that kind of continuity and a bit of a smoothness to it, essentially. Then if you want to find that definite integral, you take the antiderivative from the lower bound to higher bound like that. And that's what this theorem says. Now we can perform some algebraic manipulation on this thing. And essentially we just add f of a to both sides. Big F of a. And we get this. This means that you can take a start value, add some stuff to it, and get your final value of the function. It's sometimes referred to as the start plus accumulation method. Because you take your starting value, you figure out how much area you kind of added, and then that gets you your end zone. That's why it's called the start plus accumulation method. You take your start, you add the amount you accumulate with that added area, and it's a method because that's a way of proceeding. So we've got a couple examples of doing that. And here we go. We're going from an x value of 0 to an x value of 2. So in this scenario, it's kind of like the b value, the higher value is a 2, and the a value, the lower value, is a 0. So a way to set this up with this particular model is to say that g of 2 is equal to g of 0 plus a definite integral. And that is essentially from 0 to 2 of the derivative of g. So 6x squared minus 4x dx. And then we're just kind of evaluating stuff. G of 2, still don't have a hot clue. Still wish this iPad didn't have dead spots on its screen. G of 0 we were given, that's 3. And then this particular definite integral, all right, its antiderivative is 2x cubed minus 2x squared, and we're going to take that from 0 to 2. Note that this 3 is not involved in that antiderivative. It's not part of that bonus evaluation part. It's not part of this 0 to 2. So it doesn't get factored into that part. This is separate. So when we calculate this, g of 2 is 3 plus whatever this brickety bracket section gives us. So that'll be 2 times 2 cubed minus 2 times 2 squared. And we're going to take that and subtract what we get with that expression when we plug in 0. 2 times 0 cubed minus 2 times 0 squared. And we get numbers out here. So 3 plus whatever this is. 2 cubed is 8, so okay, 16 minus 8 minus a whole bunch of 0. Okay, so then it's really just 3 plus 8, which is 11. Wow, what a day. I encourage you to try this last example. And again, pause the video, give it a few minutes, give it a good, rock solid, honest effort, and see how far you get, and then proceed with playing. Wow, are you proceeding already? That's incredible. We're going to figure this thing out. We're going to go from f of 1 to figure out f of 4. F of 4 is then what we have with our start value plus the accumulation. Oh, I keep doing this. Not f of negative 1. F of 1 plus the accumulation. The accumulation goes from an x value of 1 to an x value of 4 for this particular function. I might write this 1 over root x as x to the negative half, just because for my own head brain, it makes it easier for me to anti-differentiate. I find it harder to do from roots, just straight up. Okay. So f of 4 is, f of 1 is negative 1. And then the antiderivative of this thing is, it's going to involve x to the half. Must have been a 2 in front, since 2 times a half will give me the 1 coefficient out there. Okay. And then 2x came from x squared. And we're taking this from x is 1 to x is 4. Now it's just a plug-in thing. Negative 1 plus what we get when we plug in 4 to this. So 2 times 4 to the 1/2 plus 4 squared minus what we get when we plug 1 into that thing. 2 times 1 to the 1/2 plus 1 squared. And if you want, I mean, you could write these powers of 1/2 as square roots again, if that tickles your fancy, if it's easier to read that way, then I would do that. I would actually just do that straight up in this very step that I just wrote. In any case, you do have to evaluate. So negative 1 plus this whole thing is stuff. 2 times the square root of 4, so that's 4, plus 16 is 20. And then this whole thing, we are subtracting 2 times 1 plus 1. So subtracting 3. Therefore, f of 4 is equal to, looks like 16 to me. Huzzah! Well, that's the end of our Fundamental Theorem of Calculus lesson. There is some suggested practice. I recommend working on this. It may bring you happiness and joy. Who am I kidding? It's math. Of course it's going to bring you happiness and joy. Miss you so much. Tell someone around you right now something that you appreciate about them. And then work with each other on this mathy math. See you in